sacrifice for the sake of science, right? It's not. Okay, you good? You're comfortable? You're really comfortable, right?
Wonderful.
Okay. You ready?
Yes.
Okay. Okay. 185.7. Stay where you are. 185.7. I'm sure I want to first make the subtraction, right? 185.7 plus or minus 0.1 centimeter. Oh, that is 5. That is 2.5 plus or minus 0.2 centimeters. You're about 1 inch taller when you sleep than when you stand up. My grandmother was right. She's always right. Can you get off here? I want you to appreciate that the accuracy, thank you very much, Zach, that the accuracy of 1 millimeter was more than sufficient to make the case. If the accuracy in my measurement would have been much less, this measurement would not have been convincing at all. So whenever you make a measurement, you must know the uncertainty, otherwise it is meaningless. Galileo Galilei asked himself the question, why are mammals as large as they are and not much larger? He had a very clever reasoning which I've never seen in print, but it comes down to the fact that he argued that if the mammal becomes too massive, that the bones will break. And he thought that that was a limiting factor. Even though I've never seen his reasoning in print, I will try to reconstruct it, what could have gone through his head. Here is a mammal. And this is one of the 4 legs of the mammal. And this mammal has a size S. And what I mean by that is a mouse is yay big and a cat is yay big. That's what I mean by size. Very crudely defined. The mass of the mammal is m, and this mammal has a thigh bone, which we call the femur, which is here. And the femur, of course, carries the body to a large extent. And let's assume that the femur has a length L and has a thickness D. Here is a femur. This is what a femur approximately looks like. So this would be the length of the femur. And this would be the thickness, D. And this would be the cross-sectional area, A. I'm now going to take you through what we call in physics a scaling argument. I would argue that the length of the femur must be proportional to the size of the animal. That's completely plausible. If an animal is 4 times larger than another, you would need 4 times longer legs. And that's all this is saying. It's very reasonable. It is also very reasonable that the mass of an animal is proportional to the 3rd power of the size, because that's related to its volume. And so if it's related to the 3rd power of the size, it must also be proportional to the 3rd power of the length of the femur, because of this relationship. Okay, that's one. Now comes the argument. Pressure on the femur is proportional to the weight of the animal divided by the cross-section A of the femur. That's what pressure is. And that is the mass of the animal. That's proportional to the mass of the animal divided by d squared. Because we want the area here. It's proportional to d squared. Now follow me closely. If the pressure is higher than a certain level, the bones will break. Therefore, for an animal not to break its bones, when the mass goes up by a certain factor, say a factor of 4, in order for the bones not to break, d squared must also go up by a factor of 4. That's a key argument in the scaling here. You really have to think that through carefully. Therefore, I would argue that the mass must be proportional to d squared. This is the breaking argument. Now compare these two. the mass is proportional to the length of the femur to the power 3 and to the thickness of the femur to the power 2. Therefore, the thickness of the femur to the power 2 must be proportional to the length L, and therefore the thickness of the femur must be proportional to L to the power 3/2. A very interesting result. What is this result telling you? It tells you that if I have two animals, and one is 10 times larger than the other, that S is 10 times larger. That the lengths of the legs are 10 times larger, but that the thickness of the femur is 30 times larger, because it is L to the power 3/2. If I were to compare a mouse with an elephant is about 100 times larger in size. So the length of the femur of the elephant would be 100 times larger than that of a mouse. But the thickness of the femur would have to be 1,000 times larger. And that may have convinced Galileo Galilei that that's the reason why the largest animals are as large as they are. Because clearly, if you increase the mass, there comes a time that the thickness of the bones is the same as the length of the bones. You're all made of bones, and that is biologically not feasible. And so there is a limit somewhere set by this scaling law. Well, I wanted to bring this to a test. After all, I brought my grandmother's statement to a test, so why not bring in Galileo Galilei's statement to a test? And so I went to Harvard, where they have a beautiful collection of femurs, and I asked them for the femur of a raccoon and a horse. A raccoon is this big. A horse is about 4 times bigger. So the length of the femur of a horse must be about 4 times the length of the raccoon. Close. So I was not surprised. Then I measured the thickness, and I said to myself, aha, if the length is 4 times higher, then the thickness has to be 8 times higher if this holds. And what I'm going to plot for you, you will see that shortly, is d divided by L versus L. And that, of course, must be proportional to L to the power 1/2. I bring 1 L here. So if I compare the horse and I compare the raccoon, I would argue that the thickness divided by the length of the femur for the horse must be the square root of 4, twice as much as that of the raccoon. And so I was very anxious to plot that, and I did that, and I show you the result. Here is my first result. So we see there d over L. I explained to you why I prefer that to plot it. And here you see the length. You see here the raccoon, and you see the horse. And if you look carefully, then the d over L for the horse is only about 1.5 times larger than the raccoon. Well, I wasn't too disappointed. 1.5 is not 2, but it is in the right direction. The horse clearly has a larger value for d over L than the raccoon. I realized I needed more data, so I went back to Harvard. I said, look, I need a smaller animal, an opossum maybe a rat, maybe a mouse. And they said, okay. They gave me 3 more bones. They gave me an antelope, which is actually a little larger than the raccoon, and they gave me an opossum, and they gave me a mouse. Here is the bone of the antelope. Here is the one of the raccoon. Here is the one of the opossum. And now you won't believe this. This is so wonderful, so romantic. There is the mouse. Isn't that beautiful? Teeny weeny little mouse. It's only a teeny weeny little femur. And there it is. And I made the plot. I was very curious what that plot would look like. And here it is. I was shocked. I was really shocked. Because look,